This video is a video documentation of our eval board, which contains the CC100 IC and the intellectual property in the chip itself. On this board, we have an LM317 regulator, which is taking the 5-volt supply down to 1.8 and gives us a good buffer so we can actually measure the current on this board itself. In this case, the 25 megahertz clock is off, so all we get is static current. We're actually measuring across a 10 ohm resistor, and the static current we measure is 5.23 milliamps for regulator current. We'll use this number later to subtract off the static so we can actually get a true picture of what the CC100 is doing. This is a picture of the disengaged current, and of course the 25 megahertz clock is on, and after we subtract off the 5.23 milliamps, we wind up with 3.14 mils, and that's with just simply the input of the CC100 hooked across the LM317 regulator to stabilize it, and it makes a complete circuit at that point. This is the engaged current plot with the CC100 engaged. As you can see, the jumper is now installed on the CC100 board itself and essentially connecting the output to the supply line. 25 megahertz clock is on. After we subtract off the 5.23 milliamp currents, we wind up with 2.72 milliamps engaged current. We take these numbers, the math is relatively straightforward. After we subtract off the 5.23 milliamps, we get 3.14 mils disengaged current minus 2.72 milliamps, which gives us 4.42 milliamps, or essentially half a milliamp of delta current. We take that number divided by the total disengaged current of 3.14 milliamps times 100, which gives us 13.3% reduction in power and current. This is a spectral plot of that board's power supply plane, if you will, and the green green spikes are actually with us disengaged. The blue plots are with us engaged, and when we do a blink comparison, you see a substantial reduction in spectral energy, which is exactly how we're saving power in these systems. We're literally reducing the amount of spectral energy that's there and feeding it back as usable power. We are Current RF. The website's www.currentrf.com. My name is Michael Hopkins. My email address is michael.hopkins@currentrf.com. And we'd be more than happy to demonstrate this in your systems and get the ball rolling by sending you a demo board so you can actually evaluate this for yourself. Thank you very much. Have a good evening.